Alright, let's start by quickly explaining what TRPO actually is and why it is even worth using in the first place. So, TRPO stands for Trust Region Policy Optimization. It's a policy optimization method that was proposed back in 2015 by Schulman and others, and what they tried to solve was one of the common problems in reinforcement learning: instability during training. When you use regular policy grading methods, sometimes the policy updates can be too aggressive. That ends up causing performance to drop sharply or just fail to improve in a consistent way. And TRPO avoids that by putting a constraint on how much the policy is allowed to change in each update. That constraint is based on KL divergence and it keeps things stable. Now, what is the key idea here? We want to improve the policy, yes, but only inside a certain region, a region we can trust. That's why it is called a trust region. If the change we make to the policy stays within this region, then the theoretical assumptions we make during training are still okay to use. And what that's what allows TRPO to make performance improvements without the risk of making things worse. And let's look at the trust region ID in more detail. What we see here is a simple policy update visualization. And the point marked as the current policy is where we are right now. The dashed circle around it, that's the trust region. Any update that stays inside this region is considered safe. So when we move to a new policy within that boundary, like the one marked as updated policy, we are confident the update won't break performance. Now, on the other hand, if we try to a bigger step, like this red arrow pointing to a policy further away, we go outside the trust region, and that can be risky. We are stepping into an area where our approximations about the value function, the advantage estimates, and so on might no longer hold. So that kind of update can actually reduce performance instead of improving it. And this is a core mechanism that keeps TRPO stable. And it stops the algorithm from doing anything too drastic in a single step. And so, why does this trust region even matter? It is because plain policy gradient methods don't have any guardrails. They might take a big step in parameter space, end up somewhere that actually performs worse, and sometimes a lot worse. TRPO avoids that by forcing updates to stay within a small, reliable neighborhood, again defined by KL divergence. Now, how does this work practically? First, we define a small region around our current policy. Then we look for the best possible update that still stays inside that region. This way we improve performance while making sure we don't overstep. That's how TRPO gets its stability. And this last note here is important. By keeping updates small and safe, we avoid situations where the agent just collapses, something that's very common with naive gradient methods, especially in more sensitive environments. Now, let's look at the objective function used in TRPO. The goal is to maximize the performance of the policy. That part's simple. We write it as J of theta, where theta represents the parameters of the policy. But, and this is where TRPO is different, there is a constraint. Okay, we don't just update the policy in any direction. The constraint says that the KL divergence between the old policy and the new one has to stay below a certain threshold delta, and this delta is typically a small value and it keeps the update conservative. to understand what is being optimized, take a look at the surrogate objective. This is an expectation of actions and states sampled from the old policy. The key part here is the ratio of the new policy to the old policy that's used to reweight and attention estimate. If that ratio gets too large, the update can become unstable, which is exactly what the trust region is there to prevent. And right below that, we have got the KL divergence formula. You can see here, it is just the expected value of the KL divergence between the action distributions under old and the new policy for each state. And again, the point is to keep this value under control. Otherwise, we risk moving too far and losing stability. And algorithm steps. As always, we start by initializing the new policy parameters, usually just some neural network weights, theta 0. That's our starting point. From there, each iteration goes through a few steps, and first we collect trajectories using the current policy. These are the rollouts, the data we need to learn from. Then we calculate advantage based on those trajectories. This tells us how much better or worse each action was compared to the expected baseline. And next, we compute the gradient of the surrogate objective. And this gives us the direction in parameter space where performance is expected to improve. But instead of updating the parameters directly, we do something else. We calculate the Fisher information matrix, and this captures how sensitive the policy is to changes in its parameters. Then comes the conjugate gradient step. We use that to solve for the natural gradient direction without actually inverting the Fisher matrix, which would be too expensive. Once we have the direction, we compute the step size beta, and this depends on how big of a step we can take while still respecting the KL constraint. After that, we do the actual update. Theta new equals theta old plus beta times the direction. And there is a check. If the new policy violates the KL constraint, we shrink the step size and try again. This last step is what enforces the trust region constraint during the update. And conjugate gradient is here. Okay. Here the idea is, instead of directly inverting the Fisher information matrix, we solve the linear system using an iterative approach. We want to find a direction that satisfies fx equal g, where f is the Fisher matrix and g is the policy gradient. Okay. To do that, we initialize everything with 0 for x0 and set the residual and search direction to the gradient. Then we go through several steps, update x, recalculate the residual, and adjust the direction. This loop continues until the results convergence. Now, why do we even bother with conjugate gradient? Well, if we try to compute the inverse of f directly, that would take a cubic time in terms of the number of parameters, which is not realistic for most neural networks. On top of that, the matrix might not even be well conditioned. And CG here gives us a way around this. It only needs us to be able to multiply f with a vector, and that's something we can do efficiently by using the Fisher vector product trick. Also, it usually converges in way fewer steps than you would think, often well before reaching the number of parameters. So it is a smart way to get what we need without overloading the system. And alright, that's okay. Once we have got the step direction using conjugate gradient, the next part is figuring out how far to go in that direction, and this is where line search comes in. Let's scroll. Now, in theory, the step we compute should give us a performance boost, but in practice things can get messy. The approximation we used earlier might not hold up for large steps. So what we do is we start with the full step and then we test it. If the new policy after applying that step satisfies the KL constraint and actually improves the objective, then we are good. We go ahead with the update. But if not, we scale back. We multiply the step size by 0.5 and try again. And we keep doing that until either the step satisfies the condition or we hit the max number of retries. The visualization here shows what's happening. You can see the initial step marked as beta, then smaller versions like beta multiplied, divided 2, beta divided 4, and so on. The KL boundary is marked in red, and the idea is to stay under that while still climbing up the performance curve. And comparison table again here. What are the VPG, TRPO, and PPO? And VPG is the most basic one. It just uses great interaction and updates the parameters without any constraints. That makes it easy to implement and cheap to run, but also pretty risky. It can collapse if the updates go too far. TRPO, on the other hand, puts a hard limit on how much the policy is allowed to change. It uses second-order optimization, which is heavier, but you get the benefit of more stable and reliable updates. The trade-off is computational complexity and implementation efforts. It is not the easiest thing to code up from scratch. Then there is PPO, proximal policy optimization, we will look at, and it is kind of a middle ground. Instead of hard constraints, it uses a clipped objective function, and that makes it lighter than TRPO, and it is easier to implement too. You can also reuse data for multiple epochs, which improves sample efficiency. So, to sum it up, VPG is fast but unstable, TRPO is stable but heavy, and PPO somewhere in between, balancing practically and safety. So now that we have seen how TRPO works and how it compares to other methods, let's go over some quick notes on when it makes sense to use it. One of the clearest strengths of TRPO is its stability. It performs reliably across a range of tasks, especially environments where performance drops are costly or hard to recover from. It also comes with a solid theoretical base. The translation mechanism has a mathematical foundation that's been proven to prevent performance collapse. And it is less sensitive to hyperparameters compared to some other methods which can save time during tuning. And it works well with different neural network setups too, so whether you are using feed-forward networks or larger architectures, TRPO tends to hold up, but it is not perfect. Right? The biggest challenge is its complexity. The conjugate gradient part and the Fisher vector products require extra care when implementing. You also need to store and process large batches of trajectory data, and if you are trying to use this with RNNs or other more advanced models, compatibility can be tricky. Plus, it is not the most sample efficient algorithm out there, so you will often need bigger batches just to get consistent results. And here critical parameters and some implementation tips. Let's quickly look at first parameters and KL divergence constraint. Delta is usually set between 0.01 and 0.05. That controls how much your policy is allowed to shift per update. And discount factor gamma is often set to 0.99. That works well in most environments, and for the GAE parameter lambda, 0.95 is a typical choice. And these values help control the balance between bias and variance in your advantage estimates. For conjugated gradient part, you don't need to run it forever. Around 10 to 20 iterations is usually enough, and adding a small damping factor like 0.1 can also help with numerical stability. On the coding side, use automatic differentiation. It saves a lot of time when computing gradients and feature vector products. And be careful with the stopping criteria for conjugate gradient. Use line search to make sure each update is actually improving performance and staying with the KL boundary. And it also helps to normalize your entrance values that can reduce variance and lead to smoother updates. And if you are short on time or computational power, it's completely fine to start with an existing TRPO implementation. And here, OpenAI's baselines repo is a decent preference. Or if you just want something easier to manage, you can consider PPO instead. It is simpler and still quite stable in practice. And that's all for TRPO, and thank you for listening.